So thanks for the organizers for having invited me to give this talk today. And also thanks everyone for being here. So my talk will be, in essence, looking at some of the questions that was already talked about in talks such as Remy Jiao's talk. So let me dive in quickly and try to motivate what I'm trying to do. So the first stop is the trichotomy in DCF0. So you've seen it several times already, but let me write it down. It's one of the most beautiful results, so it's okay to write it down a lot. So, let X be a strongly minimal set in DCF0. So from now on, I'll mostly say SM. Then exactly one of the following holds. Either you'll be non-orthogonal to the constants of your differential field or differentially closed field, or you'll be non-orthogonal to the Manning kernel of some abelian varieties not over the constant. And the last case is X is geometrically trivial. So now we've seen this as well in Kobe's talk, Peter Pedersen's talk. And so also I'd like to mention that in Remy's talk, this was disintegrated. So same thing. And really, the trichotomy gives us nice ways by which we can look at the non-trivial strongly minimal set. When it comes to trivial one, while geometric triviality really limit the complexity of the definable set, given one such set, one still need to do something. We need to sort of try to determine what the exact induced structure is. And so it's been long a desire of those working in model theory to be able to, instead of to fully be able to, that the trichotomy fully says what the structure is. And a candidate for a long time was omega categoricity. So let's say that X is definable over K, strongly minimal, and geometrically trivial. Then X is omega categorical if for any y, if you look at the algebraic closure of an element, and you look at those elements of X that are algebraic, you get that it's finite. So this says that there's not very much structure for the strongly minimal set. And an old conjecture which is now known to be not true generally, was that one can replace 3 here by omega categorical. That also was mentioned is so Ruszowski had shown that this is true for order 1 definable set. And I would say that the question is still open for order 2 strongly minimal set, if you're trivial or you're omega categorical. But the key thing here is that a counterexample, and again that was in Remy's talk and also talked about in Jonathan Pillar's talk was that the J function, the third order ODE of a J function. And so this, in a way, was a little bit, for me personally, sad that the conjecture wasn't true. But what I want to argue today is actually that the J function is within a class or even in a family of ODEs where actually we can classify, we might be able to classify when the sets are omega categorical or not. So argue that J functions ODE is in a class or family of ODE where triviality can be classified. And here the idea would be when omega categoricity is true or not, one can exactly say what would be the case. Okay, so I'll now spend some time talking about Fuchsian groups and their uniformizing function. So I'll have, so gamma will be a discrete subgroup of PSL to R, so a Fuchsian group. So I'll also denote by P gamma the set of cusps of gamma. So these are elements of the upper half plane where you add the projective real line, which are fixed by infinitely many elements of gamma. Cannot read? You said it. Yeah, so I said it. So I'm just elements of the upper half planes where you add the projective real line, which are fixed by infinitely many elements of gamma. So what we have is that gamma acts on H star by linear fractional transformation, as we've seen in Jonathan's talk. Say it again? Yes, gamma, thank you. And so under this action, the quotient of H star with gamma is a compact Riemann surface. And my assumptions are that the Riemann surface is of genus 0. In a while, we'll see why I need the genus 0 assumption. So compact Riemann surface. So this is a non-trivial assumption. It means that we're looking at Fuchsian groups of Skine, and that, as I said, genus 0. And so with gamma, we have a projective curve. So we have a projective curve which I denote by chi gamma, and of genus 0. And the functional field of this curve is isomorphic to the field of automorphic function for gamma. And as we have a genus 0 curve, it's generated by one function called the Hauptmodul for gamma. So let's just say that all that I said is that we can take J gamma. So the choice of J gamma is not unique. And so J gamma is a moromorphic map from H star to chi gamma. So it's a covering map, and as I said, automorphic for gamma. So okay, so in a very similar situation as the J function, which indeed is an example of this map. Say that again? Yes, I think so. Yeah. And so what's important for us, the key for us, is that these J's satisfy ODE of third order. These are the same that of the same form that Jonathan had on the board. So J satisfy ODE of Schwarzian theorem. So we had this on the board on Tuesday. And let me call this equation, I can do that here, star J gamma, all right? So the equation, so this is the rational function. This is a rational function of y depends on the choice of the generator. So one can choose various kinds of generators. And here, for technical reason, there are non-constant solutions of this equation. So where ds here is the Schwarzian derivation. So at this point, I think it's also important to mention that this is again a special case of a more general phenomenon, what can be found in the work of Tom Scanlon, about covering maps and generalized Swartzian equation that the maps satisfy, right? And few things we know about them. So that's due to Nishioka, is that the J gamma is a generic solution of the equation. And a second one, which the proof is the same as for the J function, is that all the solution of the equation is of the form okay, so in a sense, the families that I want to point out that one maybe can classify when they are omega categorical or not will be within families of equation of that form. So what's the difference between, so far it looks very similar to the talk, few things in the talk of Jonathan. The equations look the same. We're looking at covering maps. So one difference is to note that not all these curves are Shimura curves. All right. So this really depends on whether you start the group you start with. If you start with an arithmetic group or not. So let me talk a little bit about arithmetic group. So now, it's not, so there are definitions of arithmeticity using quaternion algebra, but that would be too much to try and do here. So I'm going to write down an equivalent definition or an equivalent condition that's equivalent, but also which suit very much the setting for omega categoricity. So here's a notation. So I write with tilde here to say that gamma 1 is commensurable with gamma 2, which is to say that if the intersection of the two is finite, has finite index in both gamma 1 and gamma 2. And so the commensurator of a group gamma is all, it's going to be a subgroup of gamma. So gamma is going to be a subgroup of the commensurator of all conjugate by gamma that are commensurable with gamma. Okay, and one always have that gamma is contained in a commensurator. And so what's useful is that using the commensurator, one can then define what it means to have infinitely many correspondences, so so has infinitely many correspondences, if gamma has infinite index in its commensurator. And so here, if you think of PSL to Z, having infinitely many AK correspondences would then follow from the fact that the commensurator, gamma is large in its commensurator. So a fact by Argulis is that gamma is arithmetic, and so the curve chi gamma is Shimura if and only if chi gamma has infinitely many correspondences. Okay, so this was a quick review of Fuchsian groups. And so now that allows me to state what the main problem is. No, so that's I did say that the definition of arithmetic is a little bit involved, and I wanted to give an equivalent property that, and here it'll be okay, because if you think about, we'll talk about omega categoricity very soon, and like in the case of J function, the fact that there was infinitely many correspondences was an abstraction to omega categoricity. And so that's what the main problem would be, to describe that indeed this is the only obstruction to non-omega categoricity. So here now I work in a saturated model of this CF0, and I think of C as the constants of U. So in these problems, we are looking at concrete examples defined with a complex number, so that's enough. And I'll also denote by y j gamma the definable set and so the aim, the problem that we're looking at is we want to show that first, the definable set for any of those Fuchsian groups is strongly minimal. And so one thing important that maybe Remy briefly mentioned, but which is, I think, important to to mention, is that strongly minimality in this case will be enough to show that the definable set is geometrically trivial. And I'll say a few words about that in a second. And secondly, show that, as I mentioned already, non-omega categoricity is only obstructed by omega categoricity is only obstructed by arithmeticity of a group. So gamma is arithmetic. If and only if is not omega categorical. Yes, so it's a discrete subgroup of PSL2R. The only additional assumption is that the surface is compact and genus 0. Oh, so yeah, thanks. I forgot to point out to the genus 0 here is important that allows us to get a rational function in the differential equations. If you don't put the genus 0 assumption, then you do get a differential equation, but that's algebraic. Instead of a rational function, you have an algebraic function. Okay, so, all right, so I realized I did a mistake. I should have started there and then put those things up. So I'm going to continue on this side. But then I'm going to just say a few words about hence geometrically trivial. It seems this was a forgotten fact in the CF0. So let P be a type of the constant that's minimal, and I assume that it's order bigger than 2, so it's automatically orthogonal to the constant. Then P is trivial. So if you have a minimal type of a constant, it's automatically trivial. And that follows from, again, in the work of Hrushevsky and Sokolovit, that if you have a type over a differential field K that is minimal, locally non-trivial, locally modular, then it's non-orthogonal to a Manning kernel that's defined over the algebraic closure of K. Now, this is very useful as an example in the proof that the J function was geometrically trivial. Proving minimality, strong minimality, sufficed then, right? And so strong minimality for types of the constants is quite a strong condition. So, all right. All right, so now let's go about some results. So the third and the fourth and last part is about triangle groups. So here one want to look at hyperbolic triangle. And the data for hyperbolic triangle is alpha, beta, gamma, integers, or infinity, such that if you look at the sum of reciprocal of the integers and 0 if it's infinity, you have less than 1. And this is simply saying that the volume is less than pi. And so in pictures, let me move to the board. Yes, positive, yeah. So some fun picture to draw. So pi over beta, pi over alpha, and pi over gamma. So let's call these vertices V1, V2, V3. And so, so these in the upper half plane. And why do we also have integer infinity? You might have seen one drawing on Tuesday by Johnson, but let's draw another one. So here, let's say pi over alpha. And so either when your vertex is on the real line or at infinity, then this is when the integers, when you have infinity instead of an integer. And the point here is that there's a subgroup of, there are subgroups of PSL2R that explain how those triangles tessellate the upper half plane. And these subgroups are Fuchsian groups of genus 0 and are called triangle groups. So, and these are the ones we look at. So describe how the upper half plane is tessellated by the triangle. So let's call, well, let's look at triangle given by alpha, beta, gamma is denoted gamma, alpha, beta, gamma, and is called is a Fuchsian group, a genus 0 Fuchsian group, and called the triangle group, right?
You mean by this that all the assumptions are satisfied?
So two things. For example, in these examples, you have to add the points on the real line and the point at infinity, which are the cups. And then you see that you get a compact compact Riemann surface after you identify the sides. So all the assumptions that I've put in earlier will be satisfied. And so these are the ones we're interested. And so also we denote that by J gamma, that it's J alpha beta gamma for the Hauptmodul. Now, a few things to note here. As I said, the choice is not, there are many choices for these. And this is determined by the value of J's on each vertices. And so let me say two things. So the first thing which I just mentioned to Martin is that gamma alpha beta is compact, non-compact, if at least one of alpha beta gamma is infinity, right? So non-co-compact, yes. So some, yes. So and but what's important is we have a uniform choice of the vertices and the values of the vertices that guarantees a uniform family of differential equation. So, so there is a uniform choice of the i's and values for J on VI's so that the rational function can be uniformly returned in terms of alpha, beta, gamma. So it's not pretty. But this gives some uniformity in the definition and in trying to prove things. But note that so gamma 2, 3 infinity was really the picture that Jonathan drew last time. And so this is PSL2Z. But under the identification here, J is not the solution of that. Rather, the usual J function is simply interdefinable with under these choices of VI's and the values. Okay, so let me talk a little bit about some results that we have. So the first one is that so suppose that is non-co-compact then is strongly minimal, trivial, and non-omega categorical. And this is not surprising once the result of Tom and James Freitag, Scanlon Freitag, was once they obtained it for the J function. It's not too difficult, but there are some subtleties. So this follows from, as I said, Freitag, Scanlon, and the Axel-Lindemann Weierstrass with derivative for J. But it's important to note that not all of these non-compact co-compact groups are arithmetic subgroup of PSL2Z, right? Arithmetic. Oh. So non-compact arithmetic, that's very important. So so one has to try to find classification of all of them, and then notice that the curves are still coverings. And so I do want arithmetic. So let me do that so that we know we're talking about. So I'm talking about arithmetic and triangular group. So not all of them are subgroup of PSL2Z. But one has to simply work out that they are indeed, that the J's are indeed interalgebraic still. And then you can still apply the argument that Tom and James gives, but the J's are interalgebraic. Yeah, so the triangular J's, yeah. So it's still an interalgebraic, so with the actual J function. So that's very confusing, too many J's. So let's just say that J, alpha, beta, gamma are interalgebraic with J. And then you do obtain the same results. But note that here again we use the O-minimality setting is behind the Axel-Lindemann Weierstrass with derivative. And it's always been an aim to find a proof of the same result without O-minimality. And so the next result is a little bit more in this direction for the compact gammas. So And here, this is quite general, so we don't need the arithmeticity at the moment. So exactly one of the following hold. So we don't have strongly minimality and so triviality yet, but we know exactly what the obstruction to that is. It's compact, yeah. I think in this case you do co-compact. So let's say co-compact. Or there you have an order one, strongly minimal, definable subset Y of our definable set X, such that which is non-orthogonal to the constant. So, of course, note that here of course, that this means that the molar rank of is at most 2. So we are able to rule out, let me see. Yeah, so we are able to rule out all order 2. Yeah, so that's so hidden in the size, the strength is that there is if there's an obstruction to strong minimality, it only comes from order 1 equation. And to end, so since I'm not too far from getting rid of that, I think I'm willing to say what precisely the conjecture I'm thinking here. So at least for the compact case. So again here, compact, co-compact. Then to be expected, strongly minimal and trivial. And 2, we know already that it's the case that once you obtain triviality, the arithmetic ones will be non-omega categorical. So we have that is omega categorical if and only if gamma, alpha, beta, delta is arithmetic, is not arithmetic. So we're not there yet, but I think I'm not too far from at least asserting one and one side of the second assertion. And I'm run out of time, so I'm going to stop here.